screencast, I'm going to discuss the topics covered in Chapter 2 in the textbook. Chapter 2 will continue our discussion of models and modeling and creating logic instructions for the computers to process, but it'll also have a lot more details on flowcharting and pseudocode. So before we get too far into the details, let's talk a little bit about the overview material that we picked up from last chapter coming to this one. For starters, it's important to understand that most of this class is going to be concerned with creating a logic model or a set of instructions, much like a recipe or directions you get from Google to get from point A to point B, so that we can use those instructions or that model as a blueprint to give to another person to actually turn into source code. Source code is those logic statements converted to some programming language, which can then be compiled, executed, run from a computer, a tablet, the internet, a watch, you name it. That's the plan here. So we've kind of gotten through the first stage of this process, which is develop a methodology that we're going to use, SDLC, which is more of a rifle approach. And we're now getting to the point where we're going to start to implement some of those models that we talked about that should demonstrate the solution to the particular problem or opportunity we wish to address in the computer. Programming and logic models and technology in general requires a discipline and a professional standard, if you will, much like a plumber, an electrician, a builder has when they're working on your home. These standards are followed by all programmers, all technology people, and the expectation is those standards will be followed when you create your code, so that if someone had to get in there and fix something you're working on, they'd be able to tell that you followed the standard, and therefore they would know to look for where to look for certain things, or would understand how certain things would actually develop in the program. For example, we work and deal with standards all the time. When you drove to school to register for this class, you came down a street which was paved and had a right and a left lane. The standard in this country is to drive on the right side of the road. However, your vehicle would have done just as well on the left side of the road. In fact, over in Ireland, they do drive on the left side of the road. But the standard is the right side. When you went and made coffee this morning, you have a faucet which has two faucet handles, one for cold, one for hot. Cold being on the right side, hot being on the left. They didn't have to do it that way, but the plumber is following a standard that everyone follows. So there's things like naming conventions, the way we call programs, the way we document our logic, which are professionally standardized with all other programmers. This is the material that's not typically captured in textbooks, or if it is, it's very subtle. But we're going to make sure that we talk about this through the class, and it's going to start with this very first, or the second chapter of the textbook. This is kind of a diagram that may also shed some light on things. It kind of talks about what we've done thus far more in general than maybe standards per se. But we always have with computers typically some sort of problem or opportunity to take advantage of. And if we're writing applications, code, programs, if you will, whatever you want to call it, web pages, we typically have a model that we want to start off with that's going to be our blueprint. And then from that model, once we feel we've got everything kind of in there, we're going to give it to a programmer. It could be a web page developer. It could be a programmer for C++. It could be a programmer for Python. And they will convert that logic model into the source code statements that are used by that programming environment to run the application on the computer. All right, so again, we're right there in the area of logic model for this chapter. A logic model is an abstraction of reality. It's a perfect world. It's how we think it's supposed to work. You may find, if you do this long enough, that your logic model might be converted into source code one way by the person who's creating the app for an iPhone versus another person who's creating it for a web page in the PC versus another person who's creating it for an application running in Windows 10. They all basically will take the essential instructions of your logic model, but the way they're converted, the syntax involved, and the way it's presented will be slightly different based on the language they chose to develop the executable solution. Okay. From last time we talked about flow charting. We talked about some of the advantages. We talked about what it does, what it is. Flow charting for this class will only be in the first couple of assignments. Flow charting tends to be very good with newbies or people who've never worked with any kind of logic before, but it tends to be rather verbose. It takes a lot of time, a lot of space. It's not an easy thing to share. It's not an easy thing to grade. It's not an easy thing to give feedback to. So even though the expectation is you'll need to have some kind of knowledge on how to read a flowchart and maybe prepare one, we're going to be doing our assignments in class primarily with pseudocode. I believe the only first 2 or 3 assignments will involve flowcharting, and after that it'll just exclusively be pseudocode. We do have some flowcharting tools. We have a Lucid Chart, which is a freebie that comes with a Google educational package. You should be able to find that if you get on your Gmail accounts and then just go down to the checkerboard and look for other applications. In addition, you're also going to be able to get a copy of Visio to install on your PC at home. Visio is a product that is created by Microsoft. It's been around for a while. It's the standard for charting and creating diagrams. We have, by virtue of an agreement we've signed with Microsoft, the ability to get you that as students in this class. Since it's an online class, it becomes a little trickier than if it was just an in-person class, but you'll be hearing about this probably later this week when we can get the class roster to them and get the accounts set up. Now, as far as flowcharting goes, we've got a series of symbols, rounded rectangles, which are also called capsules, circles, rectangles, diamonds, parallelograms, and lines. All of these things do everything from, like in the case of a rectangle, allow you to put an expression that is an assignment or calculation in logic, or a diamond, which is a Boolean expression which is used for looping and if statements, and then the lines themselves connect these symbols to show the flow of information. You're going to find there's several rules we still have to abide by. The termination symbol is used to start the program with the keyword start on it, and then it's used to end the program with the word exit or end on it. You're going to find that diamonds are the only symbol that has 2 lines coming out of it. Most of these symbols have 1 line coming in, 1 line coming out. A diamond has 2. Why? Because the diamond has a Boolean expression. Boolean expressions are like an if statement that have a true and false branch. The reason they're called Boolean because there's 2 options, and with computers they're binary devices, so true, false, and Boolean's perfectly consistent with their design. So you're going to have true or false or 2 options, so therefore 2 lines. The book does a pretty good job in terms of showing the symbols, showing how they're put together, how they're connected. There's also in the Files tab of Canvas a number of examples that are in Visio or PDFs. These will also show how this technology works in terms of what symbols are appropriate, the lines that connect them, and you'll also notice there's text involved here. And as it turns out, and you'll see this from a later slide, that the text inside each symbol is roughly the equivalent of what pseudocode would look like, okay, which is just a text representation of the logic, and the one favored by this class. Advantages and disadvantages. The nice thing about flowcharting is a picture is worth 1,000 words, and typically if you're working with someone who's had no experience with logic, they will probably understand the flows in a flowchart sooner than they will understand pseudocode, which tends to look a little bit like math, which normally scares everybody half to death. The problem with it is that flowcharts, when it comes to sophisticated logic, can become very complicated to create. You almost have to be an artist the way you have to position things and place things. They tend to take up a lot of space too. It's very difficult to get any kind of complicated algorithm or set of logic statements together on a single page. You have to go multiple pages down and multiple pages to the right and left. So to actually show someone the entire diagram requires a very large table with a lot of pieces of paper. So that's a disadvantage. Here's an example here showing, again, the termination for start and stop. The parallelograms are representing input in this case, output in this case. The rectangle is used to show, at least in this example, calculation, or what's called a sequence structure, which we'll find out a little later in the book. Pseudocode, non-standard, can't be executed. But what it does do, it's like a recipe or direct directions you get from Google. It will walk you through from the start and the beginning the different steps necessary to complete the task, to tell the computer what you want to have done in English-like statements. You can't execute it, which is why we'll use Python sometimes, because we'll convert the pseudocode to Python to test it. But at least from a blueprint or a planning or a modeling standpoint, it's very effective. Advantages. Well, the first advantage is it's much like the code we're going to create. So if I give someone pseudocode, typically they can make that conversion fairly quickly. They can, especially in the case of Python, with just a few little changes, since Python doesn't have a lot of special syntax or grammar with semicolons or curly braces or braces, it can be done rather quickly. Disadvantages, well, you can't run it, so it's really just an idea still. And then secondly, if you're not a programmer or a technical person, it could be a little intimidating. These are the steps involved with creating a program. Again, it's the SDLC again, it's doing the requirements, it's getting the code together, it's creating a model, it's creating the source code statements, which are either compiled, run through an interpreter, or run through a runtime engine. Most of the time, students resist creating pseudocode. With some of the newer programming environments, especially with the .NET and Visual Studio, it's very easy to start programming. Just start write some code. That's fine, but typically what happens if you're new to programming is you'll create a whole bunch of code only to find that maybe 2/3 through the project you've got a serious issue. So what we encourage is everybody to try to diagram or model out the logic first, and we say, listen, pseudocode can be used and recycled in your programs like program comments. And all a program comment is a statement. You saw this in the first chapter, where someone can put some text that describes what that part of the program is doing. It might be for them later on, a couple years down the road. It could be for someone who's never seen the program before, to kind of help them through the logic that was in the mind of the programmer that did it. Okay, so we'd like to still encourage people to do pseudocode. You're going to have to do it for this class, but when you move on to Visual Basic or Python or C# or Java, you may be asked to do it. You may not be required to do it, but it's a good idea to do it. Just like it's a good idea to have a builder, for your builder to have a blueprint before he builds the house, rather than just hammering in nails and putting everything together and hopefully it comes out okay. The best thing about this slide is it probably shows the space required to document what amounts to the same model two different ways. Pseudocode this side, flowchart on this side. You'll also see, if you follow this, and this is a little bit tough to read in this particular size, but these PowerPoints are inside your file section in Canvas. This pseudocode text is actually found inside the symbols. So we'll dispense with the flowcharting after a couple of weeks, but it's important at least to understand how to create it and how to read it. We also will be doing and using some Python. Even in the very first chapter, I converted one of the models into Python. And the reason that Python is helpful is that, first of all, many of you need some exposure to a programming language. Python is a great one to learn from. Secondly, it doesn't have a lot of real sophisticated syntax requirements. The only thing it really cares about is that when you write the Python program, that the program starts in the first position in a line, first character position, and then when it comes to creating blocks of code or modules, which we'll get into later in this class, it wants them to be indented. It doesn't require curly braces or semicolons, which if you've taken Java or JavaScript or C#, you will have fond memories of, because that part of the syntax is not natural and tends to create a lot of problems. I think Python's a much more natural way to describe the logic so the computer can actually run it. And again, the only reason we want to learn Python is because we might want to test these models out. When I create a model for you, I may create it in pseudocode, but then I turn on and may run it for you in Python, just so you can watch it as it's moving through the code and it's executing each one of those instructions. Here is a Python program. The hash marks are comments, which are used to describe what the program is supposed to do. And the actual code for this program is just 2 lines. This first line is asking for you to enter a name. There's a prompt that appears on the screen. You use the keyboard to enter the name. It's stored in what's called a variable. Okay, and a variable is just simply a name for a location in your computer's memory. You'll refer to it in this program as name, but it's mapped to a location. The location is some hexadecimal address, 4 Fox Easy Charlie, or something, some hexadecimal address that the computer understands. You'll understand it as name, and then there will be a value. Maybe you put the name Gary in there. And then down below here it simply says print name, name which has the value of Gary. So what would happen here is that when this program ran, it would actually display the word Gary after you typed it on the keyboard. You know, there's been a lot of angst sometimes in this class about the Python. It scares people. The bottom line is, if you're taking this class, you've chosen a current technology. Sooner or later, you're going to have to do some sort of script macro programming. Python's a great one to start with. It's my favorite, and I suspect if you did a Google on it, you'd find most people start with Python. It's an up-and-coming language. It's very strongly promoted by both Google and Microsoft, two major players. It comes by default in Linux and in Apple. In the Windows environment, you have to install Python. Some of you might have Python experience. Some of you might have taken my Python class. It's a very good language to learn how to program with, and we'll be using it in this class. Do not let it intimidate you. It's there to help you. You can turn in your assignments with Python at your option. There will not be any questions on the test that I don't give you heads up on ahead of time that are Python. And even that, it won't be a whole Python. I might ask you to create a little piece of code that's maybe 4 or 5 lines long, but we'll get to that later on. We will be using what's called an IDE, an integrated development environment. These are tools that help programmers put together logic and then source code. We'll be working with program syntax. The errors we'll be looking at are syntax errors, runtime errors, and logic errors. Syntax errors are, like in the last example, that word name. If I forgot the A, the program would have failed because I didn't define what NME is. I defined what NAME, so that's a syntax error. A runtime error is when you're asking the computer to do something that doesn't make any sense. Divide by a letter, divide by 0, those kinds of problems. These will be elaborated in the future in much more detail. A logic error is the most difficult problem. These two problems will typically cause the program to crash. Logic errors may not. Maybe your calculation was supposed to divide by 3 and it divided by 2. Well, the computer will only do what you told it to do. And if you told it to, it'll do the division. It won't show up as an error. It'll give you a bad answer. But unless you catch that in the testing phase of your development, your user is going to have a program that's not going to work correctly. And that's simply a logic error. Logic errors always equate to mistakes made by the person who designed the program. Debuggers go with IDEs in that they're software tools that help, in the case of the debugger, helps the programmer find his error. Now, the word debugger or debug means to remove bugs. Bugs is a term that was initiated back post-World War II by Grace Hopper in a project she was working on. You guys can Google this. I'm not lying. And if you go to debug and Grace Hopper, you will see a picture of a gypsy moth pasted into a lab book. When they were doing some initial testing on some of the very first computers, they used vacuum tubes which emitted light. These vacuum tubes were notorious for being unreliable. They would fail all the time. So they had to keep records on why they failed. Well, on one particular occasion, a gypsy moth flew too near the light and shorted it out. So in the lab book for that evening, they comically put in there was a bug in the system, and that's what broke it. Well, it stuck. Bugs and debugging is now synonymous with errors in almost every field you can think of. And debuggers and as a programming tool for programmers helps you locate these errors before you give them out to the user, and the user finds out, and there's all kinds of problems with that. Testing and testing plans are also a critical part of creating code. When I was at IBM, we actually had a situation for every 2 errors we fixed, we created a new error. So that was a problem. So we had to get very, very deliberate in our testing, and we had to come up with test matrix, test plans with a lot of regression testing to ensure these programs are very complicated. We do not think like computers. Computers are done exactly what they're told, whereas we can take and reason and learn and do a lot of things computers cannot do. It's very easy for us, if we're not careful, to let that get into our computer programs, and that would cause it to fail. So testing is critical. Vocabulary and terms. Again, things you're likely to find on the test in the multiple choice true false section. I think that that's probably enough for today. What I will do is there'll be other videos and other resources out there for you to help you with the first 3 assignments, which encompass some of this and also some information that's in Chapter 3. Thank you.